Okay, today I want to discuss Massey Products and formal differential graded algebras. Okay, let's start from definition. A is non-negatively graded algebra connected over some field K. And we also assume that A is differential graded algebra, differential, which means that we have differential, co-chain differential, increasing degree, satisfying Leibniz rule. We have multiplication here, it's algebra, graded algebra, we have graded multiplication, of course, and differential satisfies graded Leibniz rule. Okay. We will also consider differential graded models, but it's on lecture. Now, let's consider the following question. What if we know that if we have co-chain complex, just co-chain complex over field, because we over field now, that any co-chain complex is quasi-isomorphic, no even homotopy equivalent to co-chain complex of cohomology with zero differential. Now, maybe we want consider quasi-isomorphisms which are algebras homomorphism. Yes, if we have two DGA, then map is quasi-isomorphism of DGA. If it's isomorphism on homology, on cohomology, yes, on cohomology, and of course morphism of algebras. It's homomorphism of algebras, of differential graded algebras. So yes, maybe yes, of course, of algebras, of graded algebras, and of course it's commutes with differential, so it's induced map on homology. It's map of co-chain complex and graded algebras. With definition of algebras, and then of course this is not true in general. This is true very rarely. In fact. The first exercise, easy exercise. For example, of course, you can check that as for as for weak equivalence in topology, if you have quasi-isomorphism in one direction, this does not mean that you have quasi-isomorphism in opposite direction. So, give an example of quasi-isomorphism between two algebras such that there does not exist quasi-isomorphism in the opposite direction. Of course, so if we want вылетел из головы, как по-русски-то тоже будет. Equivalence relation. If we want equivalence relation, then of course we need to close this relation with respect to symmetricity. So to DJ quasi-isomorphic to B. If there exists zigzag, yes. If there exists a zigzag, of quasi-isomorphisms of algebras. As for topological spaces, two topological spaces are weak equivalent if there exists zigzag of weak equivalences. But we know that, for example, that for topological spaces we have CW approximation, and if they are weak equivalent, if they are weak equivalent, then their CW approximations are homotopy equivalent, so we can assume that they are the same, and so we have two weak equivalents. We have zigzag of the length 2, just a roof. This is also true in algebraic context. Maybe I will tell this a moment later. Okay, but general definition is zigzag. And so we can speak. We can ask the question. If any DGA is quasi-isomorphic to, for example, DGA with zero differential, A is formal. If A is quasi-isomorphic to algebra with zero differential, because we know that quasi-isomorphisms, they preserve cohomology. This algebra must be cohomology algebra. Of course, yes, we know that if DGA, then cohomology is graded algebra because multiplication defines multiplication cohomology. So it's quasi-isomorphic to homological algebra with zero differential. What this definition. No, and so we can ask if if any algebras are formal, or if some given algebra is formal or not. Okay. No, and no, yes. No, maybe. Okay. And one, the most popular tool to understand if your algebra formal or not is the Massey products. Massey products. Now let me give a definition. Is this clear? Yes? Okay. I have two, как вот по-английски будет сказать сюжет? Вот по-русски мы говорим, у меня есть два сюжета, которые я хочу обсудить. Как по-английски сказать? I have two stories here which I want to discuss. One is about Massey products, it's abstractions to formality, and another is minimal model, it's kind of CW approximation. I will not give any proofs of them, but I just want to discuss them. Okay, the first story is about Massey products. Massey products, abstractions to formality. Not sufficient, but necessary abstractions. Okay, no definition. No, for example, the first definition is triple Massey product. If we have differential credit algebra, now we have two classes, three classes in cohomology, of some degrees. And let's assume that these products are zero of the first two and the last two classes in cohomology. Oh yes, maybe let me fix some notation. It's useful notation in this story. It's side notation. Let me denote by yes, let me denote if I have some element in my algebra, any graded algebra, then I will denote a bar is -1 a plus 1 a. I hope it's true. Okay, let's check now. Okay, now I want to then define the following thing. Okay, I have two. What does it mean? This means that UV is some coboundary, yes? And VW is some another coboundary. What? Maybe yes. I don't know. Yes. But now I want to a little bit, some traditional notation. I need to consider some signs here. No, it's also true because if it's without signs, it's coboundary. It's with signs, also coboundary. Okay. Okay. No, and then I can construct the following thing. I can construct this thing. Now let's check. Let's compute differential of this thing. I claim that this is a cocycle. No, okay, it's T bar W plus -1 T bar. No, dW is 0 because it's it's representing the cocycle of some homology class, yes, and du is also 0, so I have no sign. I only have u bar -1 u bar ds. It's minus 1 t plus 1 u bar v w plus minus 1 u minus 1 u plus 1 u v bar w. Так, is this 0 or not? Let's check. Degree of t is, no, because differential of t is u plus v, is u plus v minus 1. So here is u plus v, and here I have u and 1. No, yes, okay. And here I have 1, and I have v plus 1. And I have two opposite signs, and this is 0. So it's cocycle, and the set of the obtaining cocycle is the Massey product. Massey product of these three cocycles, such that the pairwise products are 0, is the set of all obtaining cocycles. Is the set in degree u plus v plus w minus 1 of a. It's triple Massey product. It's not one valued operation, yes? It's set valued operation. It takes three classes with this property and gives you the set of classes, set of cohomology classes. No, okay, let's. It's why it's on the next seminar. I think I will say something about topological meaning of Ellenberg-Moore spectral sequence. No, here, for example, it's famous example of so-called Borromean rings. Yes, let me draw this link. Borromean rings. No, it's this thing. Oh, here I do this right here, right? Раз, два, три, 4. And yes. Oh. This link is the Borromean rings. It's not trivial link, but any pairwise two circles are not linked. Any two, because for example these two links are not linked, and any pairwise. So if you want to prove that this thing is not trivial, you can consider the homology of the Borromean link. It's this set of the как это называется? Complement of the set, yes, and consider homology ring of the thing. And in this homology ring, in for example in some cochain ring or something like this, you have three cocycles corresponding to the for example you have two one-dimensional cocycles corresponding to the something like this, going around one circle. Okay, you have two cocycles, and pairwise products are 0. It's more or less it follows from the fact that the pairwise circles are not linked. But the triple Massey product is not trivial. In fact, it's not trivial. Oh yes, maybe I did not say what does it mean it's trivial. Massey product called trivial if this set contains 0. If the set contains 0, if you can obtain 0 in such way, then we say that Massey product is trivial. And you can check that this Massey product is not trivial this corresponds to the fact that this link is not trivial in the whole story. But any two circles are trivial. This corresponds to this property that any pairwise products are zero. So this is topological origin of this story. Because these things, I think they they started from topology, I believe, from something like this. So it's maybe topological picture. You have something which has pairwise zero, but triple thing is not zero. No, of course it's not obvious, but it's true. Okay. Now let's define the n-tuple Massey product. No, maybe two tuple Massey product. It's just product. It's always defined and one-valued operations. Triple Massey product defined only on this subset of triples of classes and not one-valued. Okay, definition of Massey product. Let's consider n homology classes. We have some represented cocycles. Let's define them AII. No, maybe yes. Maybe let's start from some homology classes, and they are represented by some cocycles. Massey product of these classes is defined if there exists defining system. What is this defining system? Defining system is the following thing. It's some extension of this co-represented cycle. It's choice of cycles, represented cycles, and another elements. Defining system. No, it's just yes, we have matrix. We have diagonal elements already, and I want all upper triangle, except of this place. I want elements Aij, where so I is not less than j, yes. No, not greater than j. Yes. No, except of not n, yes. With the following property. AII. No, for triple Massey product, I have this matrix. I have three represented cycles, and I wanted two another elements, A2 and A23, such that d bar A12 is A11 bar A22, and d A3 is A22 bar A33, something like this. And then I define Massey product as A12 bar A33 plus A11 bar A23. Now I can just generalize this. I want the following thing. I have such elements such that d of Aij is Aii bar Ai plus 1 j plus Ai plus 1 bar A plus 1 2 j to A bar I j minus 1 Ajj. such things. No, so no, yes, it's some properties of differentials. Property of the next diagonal elements is defined through the previous diagonal. Of the previous diagonal. These elements on the previous diagonal. Yeah, no, yes, on the previous diagonal and on the previous Aij, yes. Now I want to say that this is some kind of induction definition. Induction definition. Is it clear more or less? No, it's a definition, of course. No, and if I have defined a system, then I can define my Massey product as the. No, I know that all such sums are coboundaries, but I have another sum which maybe is not a coboundary. Is the if I have something like if I have a and n here. What I don't know, I don't have a and n, but if I have a n, then the differential must be something like this: a n n n. Sorry. Just 1 second. Sorry, it's not in n. Sorry, it's not in n. It's 1 n. Yes, sorry. No, because this 1 n. Yes. Then it must be 1 1 1 1 2 n plus 1 2 3 n, and so on. A bar 1 and minus 1. No, I can't. I don't. Yes, and I have. Yes, and then it's this thing. Yes, well, something like this. No, all previous such sums are coboundaries, but this sum is maybe not coboundary, and this is my definition of my Massey product. It's cocycle. It's definition of my Massey product. This is my. I don't know. It's X. You can check from this identity that this is cocycle, in fact. And this is definition. The Massey product of my classes is set of all such X from all defining systems. Note that it lies in some homology. I don't want to calculate the degree now. Okay, this is more or less direct generalization of this observation.
Could you show the matrix how we take entries for
no, okay, let's see. I have if I have ij, I want I plus 1, j, I plus 1, j. Then I have I. No, okay, let's see. For example, for I don't know for A2, for example. Okay, I don't know what the maybe yes, maybe A2 it's not interesting. Maybe no, yes, okay, yes, you're right. Let's start. If I have my diagonal, if I want to define, for example, the next diagonal. Okay, no, yes, for example, A2. A2 means that the differential of A2 must be A11 plus A22. What? And this is this all. Yes, it's from these two things. No, as for this, it's just product. Okay. No, yes, maybe on the next diagonal it's kind of the previous thing. Di I plus 1 is just I plus 1 I plus 1. It's so in fact this means that this Massey product also defined, and this is part of the triple Massey product of this diagonal. No, we know that. No, yes. Maybe you're right, yes. And this is defining system of the pairwise Massey products of these elements. No, the next diagonal is kind of the differential of the previous ones. No, for example, d a I plus 2 must be on the previous step I plus 1 I plus 2 defined on the previous step plus no, it's exactly Massey product. It's exactly Massey product. And a this thing I plus 1 I plus 2 I plus 2. It's exactly Massey product, and this means that the defining system in particular means that that products of these pairwise elements in homology are 0, and their Massey products is also trivial because these Massey products in homology, no, it contains coboundary. You're right. In particular, if you have defining system, this means that all ordered subsets also have defining system, but all these Massey products are trivial. Massey product is trivial if it contains 0. If it contains 0, we said Massey product is trivial. If some Massey product defined, no, if it's defined, if it has defined system, defined if it has defined system. If Massey product has defined system, it's defined, and if it's defined, then all sub-Massey products are trivial, defined and trivial by this, okay? Because this defining system, their ordered subsystem is defining system for the sub-Massey product, okay? We see this on these first two steps. Okay. So it's not true that no, it's not sufficient. Of course, if you have defined Massey product, that all sub-Massey products are trivial. No, it's not true that if you have some ordered set of classes such that all sub-Massey products are trivial, it's not true that Massey product is defined in general, because in fact you don't even need that all these Massey products are trivial. You also need that all this it's 0 in homology, so you have its coboundary of something, but these elements must be can be chosen in some coherent way. It's a little bit stronger than just say that all sub-Massey product is trivial, but of course it's necessary condition. Of course, necessary condition to define a higher Massey product is that all previous Massey products are trivial. But in some self-coherent way. Okay, it's definition. Now some properties. The first step is a little bit more clear now. Okay. Yes, it's true. Okay. It's your right observation that defined system ordered subsystem is defined system for ordered subsystem of cocycles for Massey products, sub-Massey product. Okay. Now some properties. They are not very hard. No, but they proved by some direct tedious calculations. No, they're tedious enough to that I don't want to do them. But I want to say them. First of all, okay, let me темнее может быть. Так, не тут. Потому что это где-то было записано, но там очень много этих самых мест. Я посмотрю. Где это может быть? Где это может быть? Ну вот, окей. Так, Massey product. Yes, trivial, defined. No, for example, of course, yes, I said that if Massey product is defined, then all sub-Massey product defined and trivial trivial if I no, if I minus j less than n. Yes, but no, opposite is not true. But for example, you say that if all submassive products not just trivial, but they are strictly trivial, they are just equals a set to only 0 class, then of course it is true. If they are equals to 0, then of course no, it's defined. So no, you have some gap between these two properties. But no, of course, if you assume this strong property, then of course it's defined. Okay, no, it's more or less follows from the definition. Okay, now
Property is not necessary.
yeah, this is necessary. If defined, then it's trivial. It means that it contains 0. But if it's equals to 0 as set, contains only 0, then of course this is defined. Of course, you can check this. No, if you want, it's no, it's more or less. No, yes, no, maybe it's not obvious, but it's true. Okay, so you have a gap between this and this. To be 0 or contain 0. Yes. Okay, then no, the first property is something like it's kind of exercise. So it's tedious, but it's doable, I think. That in fact Massey product. What we say that Massey product. No, it no, by notation, it depends on homology classes. But from definition, in our defining system, we started from represented cocycles. Now you can check that in fact these things does not depend as set, does not depend on AII. No, which means that you can start from any. You can restrict your attention on defining system which starts from any chosen set of representatives, and you obtain the same. Even if you consider only such defining system, you obtain the same set of classes. It's clear what I said. Okay, you can choose. You can fix some representatives and consider defining system only with these representatives, and then no, in fact you obtain the same set of Massey products. So in fact it depends only on homology class, or not on representatives. No, from definition it's also true, but no, it does not depend on representative at all. You can start from any representatives. No, it's useful thing. So if you have your favorite representative of some of your classes, you can start from them. Okay, it's the first property. The second property, is something like. No, for example, if you consider your classes and multiply one class by scalar from your field, what you obtained. No, it's not the same as scalar of set, but no, it contains scalar on set. No, it's more or less obvious because no, for these classes it's more or less not very hard to define defining system. So no, it follows that between no, for these classes you can define such defining system which gives you this set. No, because you can just multiply in some places by lambda, and so from some defining system of this Massey product you can obtain this set. No, this means that this inclusion. From some defining system you obtain something like this. It means that you have inclusion. Maybe it's not. Maybe you have some other defining system and you have maybe some other elements. But in fact, you have something like this. It means that what I want to say, for any defining system here, you can define defining system for this element such that the corresponding Massey product is this Massey product by lambda, multiplied by lambda. Okay. This means this inclusion. For any defining system here, you can define defining system here such that the resulting cocycle is lambda on the resulting cocycle here. It's not very hard. Important thing, the most important thing, I think, the following theorem, I think. It's not very hard, but it's tedious enough. It's the main property. No, the easy observation that if you have homomorphism of algebras, what about naturality of Massey products? If you have homomorphism of algebras, then if you have some cocycles here, then you have some cocycles here. And if this Massey product is defined, no, then in fact you have consider corresponding defining system here, just apply f, and this is defining system for this Massey product. So this Massey product is also defined. And of course, the corresponding cocycle is just f of the corresponding cocycle. So f of this contains this. All such. No, sorry, no direction. Yes, if you have some defining system here, you can apply f and obtain some cocycle for some defining system of this. You have this inclusion. If you have some defining system here, it gives you any Massey product of these elements. If you apply f, you obtain some defining system for these elements. So f of Massey product here is some Massey product of this. Maybe you have some another defining system which is not, does not come from defining system of. No, for example, if f is 0, no, it's not homomorphism of algebras, but no, if it's 0, then it's 0. Maybe it's not. No, yes, no, it's 0. It's in general it's strict inclusion. In general, it's strict inclusion, but tedious but very important calculations can tells you that if f is quasi-isomorphism, if it's isomorphism on algebra on cohomologies, then it's equality. Then quasi-isomorphism preserves Massey products. It's not very obvious from definition, but it's true. If you want to see why it's not obvious from definition, I can give you an exercise to check this for triple Massey product. Check that if quasi-isomorphism, then f of ABC is f of A, FB, FC. No, of course, it's obvious for double Massey product for multiplication. Yes, we know. But for triple Massey product, it's already not obvious. And already you need some calculations here. Already. But you can do this. In general, no, you can do this also, but with some time. So what we obtained that if two homology algebras are quasi-isomorphic, then no, they have more or less the same Massey products, what I want to say. And from this theorem, and from one another observation, what if we have zero differential in our DJ? What if our DJ has zero differential? What does it mean? No, let me give you this as an exercise. That then all Massey products are trivial. All defined Massey products, maybe they're not zero, but they're trivial. No, but no, yes, they contain zero. No, all co-boundary is zero, so are trivial. Now, for example, for triple products, we have that A2, it's d of something, but then it's 0, okay? And no, sorry, it's A2, yes? It's by definition. And A2, A3 is 0. And this means that in defining system I can choose zeros here. This means, and so for this defining system I obtain 0. No, and the same in general situation. This means that I have because I have that it's differential of something, so it's 0. So I can redefine my defined system and choose just zeros here. And so I have, in fact, I have, from this you obtain that you can choose defined system with all zeros, except of the diagonal, and this means that your Massey product is 0, contains 0. For this defined system, you obtain 0. It's not, maybe you have another defined system, but for this defined system, you obtain, and this contains 0. It's trivial. No, in fact, we proved this now. Okay, no, it's easy observation. No, and so we obtain that if differential graded algebra is formal, then all Massey products are trivial. It's what I meant when I said that this abstraction. So corollary that if A is formal, then all Massey products are trivial. So it's abstractions. If you have some non-trivial Massey product, then your algebra is not formal. It cannot be quasi-isomorphic to algebra with zero differential. In general, it's not sufficient. No, if you a little bit try, you can construct some algebra which has zero Massey product by some maybe silly reasons, but it's not formal by not very silly reasons. It's some primary abstractions for formality. For example, if you consider something like, let me say, for some example, you have algebra with 3 generators and differential acts like this. In dimension 1, 1, 1. Maybe, or in dimension, 1, 1, 1. Okay. Maybe then they are not commute. Yes, maybe it's free associative algebra. They're not commutative, not graded commutative, but okay. They skew commute because they are odd dimensional. Then you can check that you can exercise, construct non-trivial triple Massey product here, and so obtain that this algebra is not formal, for example. You can, on the other hand, you can directly check that there cannot exist quasi-isomorphism. Let me remind this example for the second. For example, now you can construct non-trivial or triple Massey product and obtain that this algebra is not formal. In some seconds, I will say another reason why this algebra is not formal. Okay. This is some calculation. You need, for any defining system here, you need redefine them to obtain this is from this. Yes. Okay. Maybe an example, geometric example of formal algebras. Yes. Maybe you heard about. Okay. For example, manifold. Okay. Okay. Manifold say that, for example, smooth manifold, compact smooth manifold, for example, say it's formal when the de-Rham algebra is formal. M is formal. For example, if you consider de-Rham algebra, it's differential graded algebra, homology is de-Rham homology, but if it's formal. Maybe you know which manifolds are formal. Complex? What complex? No, yes, of course. For example, Keller. What? It's theorem that if M is Keller, so it's complex and has, for example, coherent, complex, and symplectic structures, for example. Or it's also true for, in fact, for example, any smooth projective variety. And in fact, it's true for a little bit more general class of Moishe zone. Moishe zone or Moishe zone. I don't remember this. N, sorry. Yes? What?
I guess there is no N.
And Moishe zone. Okay, yes. Moishe zone manifolds. It's compact complex manifolds such that if you consider meromorphic functions, its field over galomorphic function, which I see because it's a compact complex manifold, and if transcendence degree of this field of this extension over C is equal to dimension of manifold, then say that's Moishe zone manifold. No, for example, Carrera Moishe zone. So in this situation, then X is X is formal. Now, how to prove this? Now, of course, we will not prove this now, but I can say one word about this. Ну да, тут всегда имеется в виду компакт. Ну, я как бы не говорю compact, of course. No, because maybe Carrera not compact, but we consider compact. No, then you just consider on complex manifold you have your Derham differential. It's sum of galomorphic differential and anti-galomorphic differential. Yes. You can consider the difference is dc. It's also different. No, okay. Yes, and no, and then you just consider the following things. For example, you consider your differential forms. You can consider dc closed forms of your X. No, you can check from the commutativity. You can check that this thing is closed with respect to D itself, and so D is differential here. You obtain some differential graded algebra, and this is also algebra. And of course, you have an inclusion if it's some forms. So any such form is some form. So it's just sub algebra, some sub differential graded algebra of all forms. You have inclusion here. Okay. And also you have projection. You can consider all DC closed. You can consider quotient by DC boundaries and obtain the homology with respect to DC with quotient differential. And theorem says that this is quasi-isomorphism, this is quasi-isomorphism, and this is zero. 3 facts. And this is isomorphism on homologies. And of course, this is morphism of algebras. And so you obtain quasi-isomorphism, and because you know this is zero, so this homology coincides with this homology because it's quasi-isomorphisms. So in fact, this is just homology of X. And this is quasi-isomorphism between them. And check that you need some kind of DDC lemmas, something like this. Yes, D bar D lemmas. Some properties of these differentials on some good manifolds to check these properties. But scheme is this scheme. You obtain this quasi-isomorphism of this form. And so you obtain that this is zigzag. It's not one quasi-isomorphism, it's just zigzag. But minimal zigzag. This is middle term. So for example, from some analytic lemmas, you can check that such manifolds are formal. It's example of formal manifolds. Some other manifolds are not formal. You can, for example, obtain some non-trivial Massey products or something like this. Okay. And now what about this example? About CW approximation, about minimal models. minimal models. It's another story. It's very important, for example, in rational homology. For example, in rational homology, you can consider topological space, and you can construct some. Oh yes, maybe I did not say this. Тут я подумаю. No, it's not important here. Yes, but here is important. For example, in rational homology theory, you can construct for any topological. No, for topological space, you have cochain differential graded algebra in coefficients with some field. For example, in coefficients in rationals in field of characteristic 0, then cochain algebra is differential graded algebra. It's not commutative, but it's no, it's not commutative. It's differential graded algebra such that the homology is rational homology of your space. But you can construct commutative algebra. And so, and yes, in fact, you can say, no, is this, no, for example, you can consider two commutative DGA, and you can ask if they quasi-isomorphic throw zigzags in commutative or in just associative algebras. No, it's kind of theorem of 21st century that is equivalent saying, in fact, but it's not obvious, but it's true. So, in fact, in this situation, you can, no, you haven't any questions here. In fact, they're just quasi-isomorphic in associative context or in commutative context. But in commutative context, you have some minimality theory of Sullivan, which I want to briefly say now. And so, no, what I want to say is that if you have space, then you have homology, chain algebra, and what Sullivan model is commutative algebra such that the homology is rational homology. It's Sullivan piecewise linear rational differential forms. And X is formal if they are formal, it's equivalent to say that they are formal. So because they are quasi-isomorphic. So no, X is formal even if this thing is quasi-isomorphic to homology with zero differential or this thing. But for commutative algebras, you have some theory to say if X is formal or not. No, rationally formal, of course. It's over Q, for example. Okay. No. And now for commutative algebra. So let yes. What if I have M is commutative, no, graded commutative, of course, differential graded algebra, it's said minimal in sense of Sullivan. This means that, no, it's, no, okay, it's connected, of course, it's connected. It's as always. Minimal means that, yes, and maybe here it's important that characteristic in characteristic 0, because in positive characteristic, no, it's much less obvious theory. It's minimal if no, it's so-called free of finite type. Free of finite type, no, means that it's free and generated by finite number of generators, finite number of odd dimensional generators, and so it's extra-real algebra, and finite number of even generators. It's polynomial algebra. It's finite number, finite. No, sorry. Finite type means that it's finite in each degree. Finite in each degree, of course. Yes. No, in each degree you have finite number of generators. They cannot concentrate it in some degree, but no, of course they can be infinite dimensional. No, and the differential of my generator lies in algebra algebra generated by the previous elements. It's definition. Not so, it's kind of observe that differential increase degree. So in fact, it's not by degree reason. It's not by degree reason, but you need that. In fact, differential. You can order your generator such that differential of some number of some generator is generated by the previous generators. Now, what for example, what if you what example to see what happens here? It's when, what for example, if we have if d of x1 is 0, what does it mean? This means that in this situation, if I have, then, for example, homology is 0 if and only if all m1 is 0. No, because no, yes. Maybe sorry. Maybe I didn't say this, but of course you ordered your generators in degrees of dimension. Of course, xk, xi, if k, no I, k, if I not greater than k. Yes, of course. It's important. Yes. You ordered your generators by degree. Is it obvious? Huh? No, let's check. No, for example, of course, no, from right to the left it's obvious, yes? From the left to the right, if I have some class, one-dimensional class, it's maybe x1. So, no, this means, in fact, that I don't have x1, yes? Because if I have x1, it's cocycle, and it must be non-zero element if x1 exists, if x1 is not 0. So, no, this means I have no x1, but if I have no x1, then by induction I don't have x2 because dx2 is generated by x1. I have no x1, so dx2 also cocycle, and if it's y-dimensional, then it cannot exist because I don't have, and so on by induction.
I mean, if we have no cocycles.
No, yes. What I have, maybe what if x1, xk are one-dimensional? Maybe they are one-dimensional.
Okay.
No, because dx1 is 0, so it's cocycle. No, by degree reason it can't be coboundary, so it doesn't exist. Because I have no homology. So it doesn't exist. So I have x2, but x2 generated by x1, so it's 0. So it's also cannot exist, and so on. So I cannot obtain. I cannot have generators in one degree. No, and in this situation, this property, in fact, equivalent to say that in this situation it's one connected situation. It's my minimal algebra is one connected. Yes, homologically connected or just connected is the same thing in this assumption. Then this property means that d dm lies in decomposable elements. it's by degree reason, in fact, no, because no, it's by degree reason, yes, because no, if I have some element, no, is it obvious? Because no, if I have some element in degree k, dmk, no, it's because no, for example, if I have x1, it may be true that yes, sorry, maybe what? It's very important things here. No, because by this definition, it's by definition x1 always 0, because I don't have yes, of course, and maybe it's something like this. Oh no, it's okay. It's ну, сейчас, что хочу сказать. And sorry, and from this you obtain that this is always 0 by definition. Sorry. Sorry. Yes. Sorry. We have this. It's in generator strictly previous generators, and then dx1 is always 0, and then this is always equivalent saying. It's one connected algebra, and if this is true, then I obtain this equivalent to say that my this property, this equivalent to say. No, it's because yes, I see that in general I have something like maybe I have something like this. In general, from this maybe it's more or less obviously that this always follows this, but this a little bit weaker because for example this situation is this but not this because I have the same number. But of course if I don't, because d of something is just one degree upper, one degree more than the source, yes, than the argument. It's degree. It's just degree plus 1. So if I don't have x1 and if I don't have one-dimensional generators at all, no, they must be. So if they are decomposable, they're decomposable of elements of strictly lower degree. So if they're decomposable, they're decomposable in strictly lower degree. What I want to say, yes? Okay. So again, if I have some element, what x, it's some y, degree y is x plus 1, and I know maybe that differential that this element is decomposable. But I know that I don't have just elements of 1 degree. So if it's decomposable, they're decomposable of some element, these elements lower than the degree of x itself. It's a, b, and degree a, b more than 1 because I don't have one element. And so they are less than number 1 minus 1, and this is x. So I have lower than x. And this is what I wanted in this situation, because that degree lower than x. Something like this. So in general, this is a little bit weaker, because I have one-dimensional situation, and maybe so I have something like this. It's increased by 1, and this increased by 1, maybe. But if I don't have one-dimensional elements, it's the same thing. It's just say that my differential is decomposable differential. It's a little bit stronger in general. So if I have one-dimensional, then I need to assume something like this. But in general, if I don't have one-dimensional generator, then it's just to say that my differential is decomposable. Okay, sorry. No, yes, and the theorem of Sullivan, yes. That maybe it's Sullivan and of Galperian, maybe. That theorem no, yes, maybe definition. No, so for algebra, its minimal model, its minimal algebra and quasi-isomorphism. It's a CW approximation. It's minimal. It's minimal model in sense of Sullivan. No, and so a theorem that any algebra in some sense has minimal model. No, no, yes. If your algebra even not connected, even homologically connected, but commutative differential graded algebra in characteristic 0 and homologically of finite type, that dimensions of all cohomology are finite, then there exists unique up to isomorphism, the minimal model. And it's natural as for CW approximation in topology, it's natural in the following sense that if I have morphism of algebras, I have morphism of minimal models. No, maybe yes, something like this. For any morphism of algebra exists morphism of minimal model such that this diagram is commuting. No, and the final observation that that any quasi-isomorphism between minimal models is isomorphisms. So no, it's equivalent to say that if quasi-isomorphism, then HF is isomorphism. No, in fact, it's equivalent to say that quasi-isomorphism for minimal it's isomorphism. So minimal algebra, they are minimal in sense that they are determined by their homology. If you have quasi-isomorphism, that in fact it's only isomorphism. No, as for CW approximation, if you have weak equivalence between CW spaces, that it's gammotic equivalence. In fact, it's a kind of Whitehead theorem. So, yes. No, and so if you have zigzag of quasi-isomorphisms, you have a zigzag of minimal models, but they all isomorphic. So in fact, you have a roof. If you have quasi-isomorphic algebras, you have the same minimal model, and you have quasi-isomorphism here. So in fact, any zigzag is no, and in fact, this algebra is minimal. You can check that. No, you can check that this is minimal algebra. If you numbered 1 to 3, then 3 is 1 and 2. So its algebra is minimal. And from Sullivan and Halperian theorem, from the theorem, you see that in fact, if it's formal, if it's quasi-isomorphic to with homology, then it's isomorphic to homology. So you need to obtain the just isomorphism with homology, but they're not isomorphic in general. Стоп, что-то я, может быть, вас обманываю. Секунду, 1 second. No, нет, все нормально, окей. Я понял. No, yes. But there exists example of, for example, minimal algebra such that it's not formal. No, it's not isomorphic to homology, but does not contain non-trivial Massey products. By some silly degree reasons, you don't have non-zero Massey products. But no, you also can see that this algebra is not isomorphic to the homology. No, maybe even you even can try to construct this. You construct model of this theorem. You can construct minimal algebra such that M is not isomorphic to this homology, so it's not formal, but all Massey products are trivial by some degree reasons. No, it exists. So not formal. No, in general, if algebra is formal, that does not mean that you have quasi-isomorphic to homology or quasi-isomorphic from homology. You even have zigzag with of this form. Maybe you don't have quasi-isomorphic in both directions. Maybe they does not exist. You only have zigzag through minimal model. So I think, okay, let's stop here.